Good afternoon. Before we start, there's a participant list that you need to fill in, and it'll be circulated in the room. Please fill in all the requested information and sign it. I would also like to inform you that the event will be broadcast live through the official Technical University of Crete and EURECA-PRO. Is it low? The volume? Up. Very interesting effect, but not for this occasion. So the seminar is broadcast live through the official Technical University of Crete and EURECA-PRO Facebook pages, and is recorded. And photographic material will be taken. All this material that we will collect will be displayed on the websites and on the official channels of the Technical University of Crete and the European EURECA-PRO, and will be published on social media, press releases and newsletters. For any issue which concerns your personal data, you can be informed through the page with Technical University of Crete's privacy policy. The Technical University of Crete and the EURECA-PRO, European University on Responsible Consumption and Production, are happy to welcome Dr. Gregory Möller, Professor of Environmental Chemistry and Toxicology at the University of Idaho in the US, to deliver a lecture, part of our series of open scientific lectures in the context of faculty exchange visits. The lecture is titled Decarbonizing the Water Sector, Biochar-Integrated Advanced Water Treatment as a Transversal Negative Emissions Technology. I would like to now invite Professor Emeritus of the School of Chemical and Environmental Engineering here at the Technical University of Crete, Dr. Ivan Diamantopoulos, to give a short introduction about our guest speaker. Thank you.
We are very excited to have Professor Greg Möller here at the Technical University of Crete, and this is your second visit here. The previous one was almost 20 years ago. I hope this is not the final one, and we have the opportunity to see you again sooner or later. Now, Professor Möller is a professor in the Soil and Water Systems Department and the Chemical and Biological Engineering Department at the University of Idaho, with a joint appointment at the Washington State University, and he received his PhD from the University of California at Davis. He teaches courses in sustainability, toxicology, risk assessment, and global health. His research explores advanced water treatment engineering, working with nature and not against it. Professor Möller has 6 of his water technology patents commercialized, with about 120 installed municipal and industrial systems on 3 continents. He's a fellow of the United States National Academy of Inventors and the recipient of the Water Environment Federation Harrison Prescott Eddy Research Medal. Professor Möller has been teaching online since the early 1990s, before I'm not sure if I can say the proper discovery, or at least the use of the web. Working with over 100 scholars and filmmakers across the globe, he created his documentary style online open course Principle of Sustainability, styled as a digital Aristotelian peripatetic school based on his studies in Greece during a Fulbright fellowship that was almost 20 years ago. One of the 40 presentations in this course, A Planet in Peril, is the recipient of the El Capitan Award at the Yomesite International Environmental Film Festival. Professor Möller was recognized with the National Excellence in Teaching Award from the Association of Public and Land-Grant Universities, whose membership represents the largest 250 universities in the US. should have brought my glasses, I have to say. Greg, it is an honor to have you here today. The floor is yours, and please keep in mind that you are addressing a wider audience, since the Technical University of Crete is a member of one of the privileged European University Alliances, the EURECA-PRO.
Thank you very much. Thank you so much, and thank you all for being here. Thank you especially to Technical University of Crete and to the EURECA-PRO partners. I've learned much about in the past months in terms of this very, what I'll call next generation program in how we teach sustainability and to be quite honest, how we change the world. If I go back to our first slide, if you want to change screens. That's good. So today we're going to be talking about decarbonizing the water sector, and in particular we're going to talk about practical technologies, and it's a platform of technologies that we've worked with for about two decades actually. What today we're going to present is Biochar-Integrated advanced water treatment, and we're going to present it as a transversal negative emissions technology. And for those of you involved in sustainability and in engineering and the general sciences, we know that we have to do more about negative emissions in terms of our climate future. So here's today for our challenge. What we've got is a series of 17 sustainable development goals that we as a society have adopted over the next several decades to achieve. These are achievements that will help us as humans and help the human condition, as well as planetary health as well. But to get to that, we need to think differently. We need to work with what is rightly so in terms of the EURECA-PRO mission, articulated as a transversal or a coming together of many disciplines and many ideas across the sciences, whether it be the social sciences. We need poets and artists to be talking to engineers and scientists, and we need to be, as a society, talking to people better than we do today. So what can we do as a society in terms of bringing all of our academic experience and all the power and passion that we have in faculty and students and our publics that we serve, and to be quite honest, get compensated for in terms of sustaining academia and our acquisition of new knowledge? How can we bring that together? How can we explore transversality as a whole system architecture to address many of these things in my field, which is advanced water treatment? So how do we do that? Well, I'd like to actually put this up here because a few years back I was a participant, in fact, one of the final four in new technologies that were being stimulated by what then was called the Barley Prize or the Everglades Foundation $10 million.
Could you move
Yes.
to the right? Because some people move there. I don't think they can see
That's all right. And so it helps to kind of focus resources on these next generation challenges. So the Everglades Foundation, very well funded, created a $10 million prize called the Barley Prize from a donor and said, come up with new ways to address, in their context, harmful algae pollution. How do we get rid of nutrients? And in fresh water, that's a phosphorus dynamic. How do we address this? And I happened to be talking to someone, I think it was a newspaper reporter, and the words came out of my mouth that discovery is best characterized as the ascendancy of solution. And I think that's a challenge for all of us in science and engineer to understand the complete process of discovery and innovation, because as a society, we need to innovate. We need to come up with new solutions to address some of these problems. For example, in my field, nutrient pollution, 6 of the Sustainable Development Goals, the SDGs, are related to nutrients and nutrient pollution. So the cross-versality or the transversality of these problems also allow us to look across disciplines, across boundaries to address the potential and the ascendancy of solution. So I come from the University of Idaho, and we've been at this for quite some time, and we've done quite a bit in terms of trying to address pollution. And we started years and years ago, and we've graduated several technologies into the commercial sector. We call the base technology reactive filtration, and you can see in this slide many of the pictures of the installations that we have. These are typically high flow, low concentration nutrient removal systems that have been addressing some of the nutrient pollution that we see in these global maps of typically fresh water, if it's phosphorus, some of these harmful algae blooms that not only cause eutrophication and destruction of aquatic ecosystems, but that they also present us with a challenge to human health and drinking water purity. So this is not only a local problem in various communities, but it's a global problem that actually goes not only from freshwater systems, but especially to coastal marine systems. So the nutrient dynamics are a little bit different, as we know from in marine systems, but it all comes back to a nutrient pollution challenge. So we've been fairly successful, and because in partnership, you can't do things at this scale without partnership associated with industry. So we have the ability to work when we get a corporate partner, a licensee, if you will, we get the ability to do things in a bigger way, big science. And the one thing about engineering is it's very hard to break into what is referred to as civil infrastructure. In fact, early in this field, I was talking with a civil engineer who told me that if it wasn't invented by the ancient Egyptians, civil engineers don't want to hear about it. Change has been very difficult. But you also realize that civil engineers deal with creating buildings and structures that don't fall down, that don't hurt people and harm people. And so their standards are very, very high in terms of acquisition of change. So when we come with a new technology, it represents change. And in fact, the technology you see in the slide went from laboratory bench to municipal civil infrastructure in 5 years' time, which in the water sector is very rapid. It's usually at least a decade from lab bench or the bench to business dynamic. So the innovation cycle is one that is relatively slow, but in fact, our futures require that we are far more responsive as a society to these challenges that we have. Responsive not only in inventing and discovering new technologies, figuring out ways to understand the cycle of their impacts, and also the better to understand the cost to society, because that is a finite metric. So as we look at this, harmful algae blooms, as I said, are challenges that represent not only local problems, but it is in fact a global issue. And climate change is accelerating the potential and the harmfulness of some of these algae environments. So let's talk about the technologies and the basic platform that we have designed and developed. And there's a few words that I want you to follow in this presentation. One is tertiary. This is actually tertiary treatment technology, which means that if it's dealing with wastewater, which is a term I use, but it is part of the problem because we talk about waste. And I would argue that there is no natural resources that should be associated with waste. It's an opportunity, it's a water resource, and we can recycle it. But the words are tertiary and reactive filtration, which is the core kind of label for our technology. It's absorptive, and we'll talk about the importance of that. And we'll also talk about the concept of a sacrificial catalyst. Now, if you're a chemist like me, when you hear the word sacrificial catalyst, it's heresy, because catalysts aren't supposed to be sacrificial. They're supposed to be able to be reused and recycled. That may be the case with palladium and platinum sort of catalysts, but we use iron catalysts, and so we can sacrifice them because if you imagine the cost of platinum versus the cost of iron, you're talking about several orders of magnitude. So what we created and sort of understood or rewrote the book on is the role of hydrospheric oxide in iron-based chemistry associated with water, and specifically iron-coated sand. Now, let me tell you a little bit about mineralogy and iron mineralogy real quick. HFO, or hydrospheric oxide, is a very short term. If you mix iron metal salts, ferric salts typically. With water, you produce a flocculating material. It's kind of like orange cotton. The earliest stages of that is something called HFO, or hydrous ferric oxide. Now, its chemical basis is far different than more aged iron oxides. And in fact, if you can capture its reactivity and activity in that first 20 or 30 minutes, you've achieved something that you can't achieve with other iron oxides that are more aged in terms of chemical reactivity and, most importantly, adsorptivity. There's a little picture there of a soil ecosystem, and the reason I do that is because a part of what we do is we try to look out into nature and study nature and understand and respect nature, but use nature as a model. So if we mimic nature, how does nature clean water? Why is it that we can go to a well, pump the water up, and it's pretty clean in most environments? Because nature does a pretty good job of cleaning water and stripping out many of the things that we call pollutants. So if you look at some of those processes, and one of those is mineral relationships, such as various iron oxides on subsurface substrates, that's part of the cleaning mechanism. Now, what we've tried to do is take that mechanism and, as good scientists and engineers, put it into an engineering context of being able to design it so it's routine and responsible in terms of maintaining clean water for discharge, clean water for drinking on a routine and regular basis. So we put those engineering controls on, but nature is telling us how to do it. So our challenge as engineers is to create these systems that present nature in an engineered environment. And so we've done that, but we've also taken it and expanded it further. So we've done HFO reactive filtration, and we talk about the success of that particular technology. In fact, I was reading that in South Korea, about 6% of the wastewater treatment plants through the Four Great Rivers program now have this technology installed across the country to address water pollution, surface water pollution in their 4 Great Rivers. But we've taken it further. And I will tell you that we've looked at this for many years now, not as a technology, but as a system and as a platform. So we've taken this basic platform, we've tried to teach it new tricks. It's just like a Swiss Army knife. It's one knife, but it has many tools. So that's the idea, is that can you teach this technology to do new things, to address new challenges? And so what are these new challenges? Things like micropollutants, these very bioactive substances that cure our diseases in very small amounts as the medicines that we take, yet have dramatic impacts on us as humans and, unfortunately, in wildlife when it goes through a wastewater treatment system. So can we address that challenge? Can we address other challenges? In fact, can we also address mitigation of climate change and carbon dynamics associated with water, but also just associated with general carbon emissions from society? So we've worked with this not only through iron, but when you add iron, we'll talk a little bit more about this, you added ozone, you can actually develop a catalysis approach to address micropollutants in a destructive removal process. And now in our most recent technology, we can use biochar to not only address carbon dynamics, but also to address the potential recovery of nutrients from being pollutants to being part of food security. So we're trying to keep moving forward in terms of addressing these key issues of sustainability. Some little bit of background for most folks. In terms of our reactive filtration, I will tell you that it is a technology that can achieve oligotrophic levels of phosphorus in the environment. So that's below 12 parts per billion to 12 micrograms per liter. Very, very low levels. And I can assure there is no technology that has matched that in the 15, 20 years that it's been out in the marketplace. Now, it's way ahead of most regulatory guidelines in terms of discharge permits, but it's still, as you can see, a relatively simple solution. The P removal mechanism, and we'll talk a little bit more about that, but it's adsorption of phosphorus and other moieties like arsenic and some other heavy metals on this hydrospheric oxide, this orange cotton that forms and adheres to the surfaces. You can see in the picture clean sand, but also then the iron-coated sand, the orange-colored sand in the bottom. We actually use an engineered system, and what was kind of neat is that we could use something that was invented in the 1970s. These they call them continuous upflow or backwash sand filters. So this is a moving bed, and when I say moving bed sand filter, I mean slowly moving. We're talking about 1 inch an hour. So, but it's moving, the sand is moving downward and the water is moving upward. So when we take the dirty water in, it actually gets injected into the bottom of the filter and rises up. So it goes through the sand bed. Simple sand filtration, which was actually hundreds of years old. Okay, again, a natural process in terms of granular filtration. These continuously upflow filters have been used in common sand filtration for water treatment for like almost 50 years now. And its basic operation is using some bubbles, some airlift in the bottom, which drives the sand, the dirtier or particles that get driven down because the sand is going downwards, and all the particulates adhere to the sand or get pushed down by the filtration process, but then goes up through a central column assembly on an airlift. So these rising bubbles actually drive some of the sand up. At the top of these filters is a wash box. It goes through a tortuous path, it shakes all the particles loose, and it actually rejects, and you can see that by the side FE. It rejects most of the iron that's been pumped into the system. The iron is just introduced in the influent water, okay? And so it's removed, and it has great grasping tech. It has many handles, if you will, for not only particulate phosphorus and non-reactive phosphorus, but for, as well, reactive phosphorus. But I want you to understand this, that we can also modify the influent water by adding ozone, common water technique process. And so what happens is that we turn this entire sand filter into an iron-based catalytic reactor, a poor folks catalytic reactor, just by adding ozone. What else can we do? We can also, as I'll describe further, we can add biochar. The thing you need to know about biochar is it's got great potential in addressing climate change mitigation, but from a physical science point of view, it's very fragile. Its Mohs hardness, if you will, is about 1, whereas the quartz sand is about 7. So we'll talk about what happens when you start mixing that, but it's one of those wins the hardness test, and one loses, and biochar loses. So, and we can take advantage of that natural phenomenon in increasing the efficiency of the process. So let's go back to the Wayback Machine, and I'm going to say probably 40 or 50 years ago, this is a textbook representation of iron chemistry with orthophosphate, and you can see this is just a model. And the model is wrong. And we discovered, if we had a discovery, it was that it isn't about solubility product chemistry. And I taught freshman chemistry for years and years and years, and I can admit something to all the students here and to some of the faculty members that quite often when we're teaching classes or basic concepts, we lie. We misrepresent because we can't represent the full complexity of subject, so we essentially synthesize an adequate explanation. And we've done that with solubility product chemistry and freshman chemistry. And in this case, engineers that take that course, they identify solubility product chemistry as what happens when you add iron to water. But in fact, it's not that at all, and it's adsorptive chemistry. So the thick blue line down there is the concentration regime that we work with in reactive filtration. So about almost 2 orders of magnitude, but at least an order of magnitude and closer to 2 of quality of effluent results. So the idea there is that textbooks can be wrong, okay? It wasn't a great discovery or powerful discovery, but it was something that enabled the development of a technology. So in this slide, you see from a point of view of what we're doing. When we first started doing some column experiments a long time ago, in 1999, we were seeing some chemistries that we could not explain. When we scaled them up, and you see a former graduate student, she was a PhD in civil engineering, standing in front of then was an arsenic removal from drinking water experiment in the field, which arsenic in drinking water attracts a lot of public attention. We're a publicly funded university. People's interest in that and sharing our discoveries, if you will, with a problem that people can relate to, and that's one of things like arsenic in drinking water. I mean, most people recognize arsenic, as rat poison or something that should not be in drinking water. So, in this particular case, training graduate students to communicate to the public, a very important mission that we as faculty have. And the idea at that point in time is we were able to scale this up and demonstrate that on a little bit of a reactive filtration trailer for several things. And we were seeing results that no one could replicate, especially in nutrient phosphorus removal. I did a presentation in the early 2000s to a collection of nutrient professionals in water treatment. And I entitled it Absolute Phosphorus Removal, because we were seeing something that was not in the data before, and getting to lowest concentrations and doing it in a very simple, economical way. And we weren't using exotic reagents or exotic processes, but what we were using was our knowledge of advanced chemistry and how adsorption, as opposed to solubility product, was the active process in this system. We didn't know at first why we were getting such low numbers. We had to do quite a bit of modeling, some surface complexation modeling and some advanced modeling to figure out the mechanism. We finally did, and that is the aha moment. That is the ascendancy of discovery. So over time, success like that yields success in terms of grants, and so we scaled it up and we started doing these other platforms, and you can see in a clockwise order as we started going from what I call in the black and white photo in the top left of your screen, I called it the missile launcher. It was outstanding in a field that we constructed the first at-scale stationary process to demonstrate the nutrient removal. And then we got into the mobile water treatment platform business. Now, you'll see in the red staircase photo, that was our first large-scale at the end. I apologize for using non-metric units, 250,000 gallons, about 250 gallons, about 60, 70 gallons per minute facility. And the only reason we were able to build that was through cooperation with the private sector, and this fact, a city that allowed us to build a whole facility on their municipal site, as well as investors that came in that saw potential in new technologies of water treatment. And so that was a way that we could advance and accelerate a technology, because if we could not show it at high scale, at large scale, high flow, low concentration, and have engineers, third-party engineers come in, and in the US we call it kick the tires, if you will, to see and validate the technology, it wouldn't have potential to have success as a product. So we elevated that, and you'll see in the orange background slide that's kind of in the middle there, was actually up just north of Toronto in 2018-19 when we were finalists in the Barley Prize. We were actually starting the biochar water treatment process at that point in time when word got out, and the people interviewing us there are from NBC Nightly News, which in America has a viewership of 7 million people. And so, as a scientist and engineer, to be able to speak words and have 7 million people listen to what you say is a very sort of high obligation that we have in terms of addressing the publics and, to be honest, addressing our employers, the people that pay our salaries. So we've been able to not only do the good science and to work with the commercial sector in terms of advancing technologies, bringing them out into the zone of product in a rapid fashion, but also to communicate with the publics that we work with. So this is a closer look of this. I did put it on here, 10 to 20 liters per second dual reactive filtration. We also found that this reactive filtration process, for a reason we don't still understand after this many years, why each pass eliminates about 90% of the total phosphorus. We haven't been identifying what the controlling equilibria or process dynamics are. So if we put them in a serial configuration, we will get 99% removal of almost any concentration that's coming in. So that's kind of a nice thing because it allows us in regulatory science to get to low levels, very, very low levels, and even oligotrophic levels in terms of discharge concentrations. And that allows us to address nutrient pollution and harmful algae blooms. So this is something, especially I want to talk to students about directly, is one of the things that we've never mastered, but we try to, is understanding working with nature. And so this is actually the first data set that came out of the Hayden facility where we're running this at full scale, at full high flows. And so we were watching day to day what the process dynamics were like. And so down at the top, you see in the red arrow line, that was the influent coming into the system. You see it's starting to trend down. We didn't know why, but wastewater treatment plants, they vary. You know, seasonality, what happens over time. The green arrow level was the first filter and the blue arrow was the second filter. And you notice that we are quantitatively removing all of the phosphorus, total phosphorus, out of there. But it was that line of serendipity, the big yellow line, that was the aha moment. And this is an instruction to, and serendipity, in case you don't know, is it's luck, good fortune, but also the wisdom of keeping your eyes open. And we were looking at this data and spending a lot of time, and there's obviously a lot going on this. Some people had invested quite a large amount of money in building this, and for the first time we were seeing it full scale. And when you scale up, it's I call it the joy and terror of discovery. The terror being, will it work at scale? And so we didn't know what's going to happen. We took the reject iron water and threw it back into the secondary process. We did not know if it was going to release phosphorus and create problems. We didn't know it was going to upset processes or anything else. But what we realized, the aha moment in this, the discovery moment, the ascendancy of solution, was that in fact that reject discharge contained only, it used up about 19% of the absorptive capacity of the iron. So we're using the iron to polish the final effluent, but we dumped the remaining 81% back into secondary, and it acted like a primary sort of water treatment chemical. And you notice how that influent water at very large flows started trending down and down and down. And that line of serendipity is where the system, the entire wastewater treatment plant, started settling down for us and producing awesome results. And in fact, I can tell you that the days between when that line and when we drafted a patent application, which was allowed several years later, was a matter of days. It was the aha moment coupled with a patent. And the reason we patent, I always like to tell people this, is not because we want to make money, it's because commerce won't enter it. They like experiments and results, but they want to get return on their investment. And if you have an intellectual property, it allows them to gain on their investment. And so it's as simple as that. If you want it to happen, quite often intellectual property is a key to making it happen. So that's where we are with reject recycling. This was a 2018. It grew in terms of installations. It's just a few North American installations. They've multiplied. I think there's 3 continents now that this process. And again, it's a pretty simple process. We don't think of it complex at all. But we decided to make it a little bit more complex because we knew the potential of what we had. And I told you a little bit about the potential to have iron ozone catalytic oxidation. This particular work generated because I was sitting down with an investor, and this sounds like something out of a movie, and I apologize if it does. This is a true story. I was sitting having a Chinese lunch with an investor, a very wealthy individual, an angel investor, that said, "We really like what's happening. We like the ideas. We like where this technology goes." And he said the key word, "If you have any more ideas, we'd like to fund them too." That is like giving candy to a child. So I said, there happens to be an idea, and I penciled something out on a napkin. That napkin generated the cover of Water Environment Research last year. That's about a $4 million installation in Horwich, UK, by a water company addressing micropollutants. And it was the first at-scale presentation. And so what we find is that with iron and ozone, we can generate hydroxyl radicals and several other radicals that are allowed for the oxidative destructive removal of many of these micropollutants. We'll talk about the variety of things that it can address. But ozone has a powerful, it's just electrons putting into a plasma. It's pretty standard technology. It's been dismissed quite often because it is a little bit more complex and has used a lot of energy. We'll show you how we can get around that. But it is a sacrificial catalyst. In other words, we use it for nutrient removal and all the HFO, but it also is a d orbital catalyst. Most catalysts are f orbital. D orbitals are poor folks' catalysts, and we can get the same sort of reactive chemistry. And so doing it at scale, and this wasn't the best location for it. It was the location that was kind of handed to us. But it is pretty intimidating as a scientist or an engineer to walk into a facility having seen pictures and engineering diagrams, but for the first time have to face the fact that there's 2 stories of stainless steel based on an idea that you scribbled on a napkin in a Chinese restaurant. Okay, so terrifying? Yes, it is the terror of discovery. So that worked out, and that was a test cycle over a period of 2016 to 18 that included handing off the keys to the technology to just normal operators and third-party operators to see how it worked for the period of 12 months. It was a best of show success in terms of addressing not only nutrient pollution, but also micropollutant pollution. And so we're achieving most of the metrics and marks. It was the first unattended operation in terms of not being a research operation where we could sit there and know what the controls. We're still learning how to process it. But all things considered, it was a successful first trial at scale. This is, for those of you that work in micropollutants, these are hormones and antibiotics and several either polluting organic chemicals typically. It's a very difficult thing to display data because there's usually a lot of different compounds, sometimes 10, 20, 30, 40, 80 compounds that we track. They can be as simple as hormones, birth control hormones, or antibiotics that we use to kind of keep ourselves healthy, or different medical compounds that are used in hospital settings that make its way through wastewater. This is an idea that what's in the kind of yellow box there is that the majority of these are excellent, 90 plus removals. And I'm going to say in most cases, especially in a tune process, because we've included not only pilot scale results here, but also at scale results. Most of it are in the 95 to sometimes 99% removals. There are outliers across there, and they can all be explained, but this does a pretty good job of dealing with that. So there's some complexities. We can go into detail, and we can read the papers that I'll tell you about if you want to know the complexities of working with micropollutants and all these different compounds and all their limits of detection, but I won't go into that today. So let's transition now. So we've demonstrated that we can use ozone to get not only nutrient removal or nutrient phosphorus removal at state-of-the-art limits, but we can also catalytically destroy these micropollutants. And let me tell you a little bit about intellectual property, because quite often it's a race to the patent office, because he or she who gets there first gets the benefits of intellectual property. And we knew that this was so easy for us to do that somebody else could do it. And so we filed for a patent, and we beat out one of the United States national laboratories, national energy laboratories called Ames Laboratory, by 3 months. They were able to patent a subset application, but we had the primary foundational patent on this process. And that was kind of nice. We're just a small little laboratory with students, graduate students like yourselves, out there working, and we were able to outpace a national laboratory. That not only earned us a patent, then that issued in 2019 for biochar water treatment, and we'll talk about how that gets executed. But the 2 papers that we published last year, one of them earned the cover, That actually is my postdoc, Paulo Yu, who actually just accepted a faculty position at University of Wisconsin. He's being our hand model. And let me also explain why you're seeing a hand and a wine glass. That's the world's cheapest spectrometer. So that's a crystal wine glass, and your eyes are very good spectrometers. You can see particles, you can see cloudiness, and so we can actually determine quite a bit about the product quality of our water. Is it crystal clear? It sounds like it's funny to do, to hold up a wine glass full of water to the sun, but it tells us very rapidly whether or not our pilot processes out in the field are working or not. So let's talk about biochar a little bit. So biochar, it's a wonderful sort of concept that was invented 5,000 years ago by ancient Amazonia. Okay, the terra preta increased soil fertility. That's your introduction to biochar, but it's just pyrolyzed carbon. So it's agricultural waste or forestry waste. There's high surface area. If you remember from your biology classes what the inside of a plant looks like, when you carbonize it, that's what the carbon looks like. And in fact, it's been shown to mostly, in 95% of the cases, increase yields or agricultural success, not only from holding on to nutrients, but also holding on to moisture in soils and many other beneficial properties. So biochar has great promise, but as a carbonized substrate, you can see that if you were to go take some charcoal and go out in your backyard, dig a hole and bury that charcoal, you would then be sequestering that carbon for hundreds of years. So you're a part of the solution in terms of carbon sequestration. So the question is, how can we do that in a very massive way? Well, we can with technology. So it's like many other things. If we include human consumption into it, we can address the ability of addressing many of these challenges that we have in society. So this is actually something we wrote into the patent, ball milling effect. So if you inject this very fragile, frail carbon substrate into the middle of a sand bed that is moving, so you've got tons of sand above you, and you inject these particles, and we were using about 300 micron in this particular experiment. But what happens is it grinds it ball mills it to a uniform size. So you see in the light line there, that's what the influent biochar that we just inject into the water stream. It makes our water look like black ink, and it comes out clean. The biochar that gets rejected has been ball milled to a somewhat uniform size. So this kind of confirmed a thought experiment that we had, because we just mentally followed what would happen if you put biochar into the middle of a sand bed. I put this in there to make sure the engineers know that we do engineering. I'm not asking you to kind of look and follow this engineering diagram, but we typically will introduce biochar and introduce ozone and introduce iron into the process stream before injecting them into the sand filter, typically in a dual reactive filtration. The first filter takes out most of the biochar. The second filter polishes it out. And we use quantities, things like iron in normal water treatment quantities. So these aren't, we're not using large amounts of water treatment chemicals or anything else. We do modify the biochar for nutrient recovery. And what that means is we pre-treat biochar with typically ferric chloride to allow for very low level of not only phosphorus removal, but phosphorus recovery in the biochar, so we can recycle it and reclaim it and use nutrient upcycled biochar. And we've been doing this now for about 10, 12 years, and we're trying to perfect it. We're not exactly perfected yet. We're still working on it, but some of the data that we have is very encouraging. So biochar is porous, but what's nice is that we have recognized that it can be used when it picks up nutrients as an alternative fertilizer or soil amendment. The thing in terms of knowing about the potential utility of biochar is that globally, we now know that it can address 6% of annual emissions, and it amounts to about 3 billion tons of CO2e or CO2 equivalents. So it's a practical, kind of low-tech way to address carbon capture and sequestration. And again, when we sequester biochar, we put it into the ground especially, that can go for hundreds of years. One of the ways we do that and we address that is actually to go ahead and do things like life cycle assessment. And it's probably a part of the lexicon of many students in science and engineering these days. But we use SEMA-PRO because it's the most accepted approach of LCA. There's many approaches and models that you can use to address that. We use it because it's a little bit easier to throw the models together and to use it to address what we're doing and how we're doing it. So in terms of LCA, the big challenge is the second one, which is LCI data collection. That can take hours because you have to discover these input models. For us, it's about on the order of 2,200 data elements that need to go into these models. The functional unit that we use in our LCAs is 1 cubic meter of water. That's the most natural functional unit that we can use in terms of water. So there we go. So we have to do a life cycle inventory, which means we have to go out there and assess. We have to measure the power coming in. We do our pilot systems, but we have enough installed systems, including one nearby campus. We can actually go out and play with a full-scale installation. We know the parts list for that, not only in our small pilot studies, but also the parts list for the full-scale implementation. And this just shows a picture of all the various elements that we have to go in and define in terms of its resource consumption and contribution to all of the impacts that we are trying to track in LCA. So in honor for the LCA scientists, including Lucine Taslaki, who just earned her PhD in our program, who put this together, this is for a full-scale implementation at the city of Plummer, which is on the tribal reservation of the Coeur d'Alene tribe. This is about the top 99% of data elements in a network diagram. It's a very complex process, indeed, to data collect and correct a model. All models are challenging to put together, as you can imagine. When we do this, and again, there's a process diagram for the particular one up at Plummer. This is the topmost elements, the largest contributors to the overall impact. And what you can see in those red thermometer bars, those are carbon. Those are global warming potential. And you can see, we've colored them red so that you can kind of see that as being, it's enhancing global warming because it's contributing to carbon emissions, either by energy consumption or some of the materials that are used in the installation, these, such as the concrete floors to build these process installations. And so as you build it out, you're actually contributing to the problem. We'll show you that, in fact, as you go through this, you can also model what the costs are, because you can put all the pieces of the puzzle back together. You can do a 20-year cost of capital model. You can do stochastic modeling. We choose to do it with Oracle's Crystal Ball and Excel because it's very intuitive and fast to put together. And we publish those spreadsheets, not the Oracle version of the stochastic distributions that we put into their models, but people can examine the models and use them or make them better. So we try to, as best possible, and again, because we work directly with the manufacturer of installed systems, we know what our pilot system takes in terms of inputs and costs. We also know what it happens if we want to put together a cost model for a 1 million gallon per day setup. This is what our pilot system looks like, and this was in Sandpoint, Idaho. This is actually the full iron plus catalytic oxidation plus biochar. So this is what we towed around. You'll see the sign on the side if your vision is very good, but that was called the clean water machine. And just so that you know, we called it that because we do a lot of public communication. And if I went out to the publics and I said, yes, this is our iron catalytic oxidation biochar reactive filtration process, their eyes would glaze over. If I call it the clean water machine, they say, oh, I can understand clean water. And so that's the efficiency of communications with people. So when we pull into town, it's a little bit like a circus wagon, to be quite honest. We have many different technologies on this, and we can configure it like a Lego kit to what we need to address in terms of the particular water quality challenge. But that's some of the ones for this particular test. I'll give an example here, and I'm not going to go through data too much, but the pilot data from this facility, if you can see those blue bars, those are at the top 100% removal. In most cases, we're in the near total removal or just below. Again, this doesn't have reject recycling that is associated with full-scale operations, but for our pilots, we know that this is how it behaves. So we get that total phosphorus removal, and that's not only the OP, which is on the full, right-hand side of your screen, but also for total phosphorus is on the left-hand side of the screen. But we talked about food security and the ability to use our recovered materials. Again, this has been processed in a catalytic oxidation environment. I can tell you that that environment, we can run the EH, which is the millivolts, the oxidation reduction potential in this system because it's a catalytic oxidation process. We'll get well over 800 millivolts EH, sometimes over 1,000, approaching the oxidative stability of water itself, close to the sterilization. Well, the contact times for our process are sufficient for sterilization. So people worry about doing anything coating the food system that comes from a waste product, and rightfully so. We've tried to address that as much as possible. We haven't fully tested it, but this is a paper that's in review. Right now, I'll just address the conclusions, and this is using the biochar product, the nutrient upcycled biochar product from municipal wastewater. The conclusion, the results of the plant growth experiments showed that modified biochar used in a wastewater treatment process can recover nutrients and be used as a soil amendment alternative to traditional fertilizers. The 4% modified biochar used in the water treatment process showed no negative effects to lettuce growth, performance, and supplied sufficient nutrients for plant growth at nearly the same level as conventional inorganic fertilizer. These results confirm the value of iron-modified biochar for wastewater treatment and recycling of nutrients. That is a bold conclusion, and we'll have another bold conclusion here shortly. So there's potential there to address some of the food security in terms of phosphorus resources. Many of you know, and if you don't know, the world's phosphorus is an non-sustainable resource because it's a mined resource. So whether it's our generation or future generations, there's going to be limits on phosphorus fertilizer, which is linked. So we address all of the inputs associated with this process in terms of the power in and the power out. We itemize and measure everything in terms of the LCA. As we put together an LCA, and so if I focus on the network diagram, in this particular case, this is Sandpoint for our pilot process, you'll see the big green bar. And we have, by adding, in this particular case, 480 grams per cubic meter of water, we have gone carbon negative, and significantly carbon negative, over 1 kilogram CO2e per cubic meter of water. And we're talking about the entire process, all of the electrical inputs in catalytic ozonation, all the pumps, all the systems within our process. That's a big deal. So the CO2e, the global warming potential, and these are the 4 impact categories that we actually monitored. We actually have the data for 18, but we only pursued these 4. But the one that is most interest for us is global warming potential, and that's a minus 1.21 kilograms CO2e per cubic meter. That's a large amount of carbon's potential sequestration. Now here's the really good part of the data, okay? And this is what I really want you to pay attention to. This is an increasing dose as you go across the screen. So there's no dose in the red, so that's carbon positive. So we're actually contributing to the problem. But as we get to the greens, we're going carbon negative. Now the light green and the dark green is just the carbon in biochar. But some people think that the carbon that's buried in the soil actually does mineralize, and so that's called the C100, the 100-year number. So it's a little bit less, it's about 75%, but we put both data points up there to show that, in fact, as you increase the dose, you get something that we refer to as dose-dependent carbon negativity. That is a big deal, okay? If we are, in fact, ascending towards solution, we have just established that biochar used in water treatment can produce dose-dependent carbon negativity. Now, it's in our case. Will it be in all cases and all experiments in technology? No. But I encourage you all to go out, dig a hole, and bury your charcoal in the backyard and be a part of the solution. This is for actually our field pilot for increasing dose rates. And you can see that we actually, across that line, have a carbon neutral, because maybe we don't want to go carbon negative, we just want to go carbon neutral. So we can actually go to carbon neutrality. But this gives the units for global warming across the top. We go from a positive 0.13, a positive 0.2 when we increase it. We add ozonation in there. And then we go to negative CO2es, minus 1.21 kilograms per cubic meter as we go to the biochar experiment. That's a big deal, but how much does it cost? Because we have to also worry not only about life cycle impacts, but about the cost of what we do for ratepayers, for taxpayers, for people that are actually paying for these technologies in our communities. And so we were able to kind of suggest that this tertiary treatment, which just makes for cleaner water, is about 8 cents per cubic meter. And this is a pilot stage. But we can actually add the biochar. And by the way, 400 or 500 grams of biochar is about a fistful, so in a cubic meter of water. And we've done it math, and I put it postage stamps size here. It's in the publication in terms of the TEA, the techno-economic analysis, to determine costs scaling up to 1 million gallons per day. So we kind of figured this. I'm going to close by just kind of talking a little bit about this discovery and its ascendance to solution. The pathway is, in short presentations like this, and especially when we talk about fairly simple solutions, everyone says, of course, that was easy. We could do that. And we could do it in a few minutes here today. In fact, the complex path that you have to take when you incorporate the expertise of engineers that participate in the process. In our case, Martin Baker is one of our engineers that puts these processes together and actually wires them and makes them work. A soil scientist, Professor Dan Strawn, that kind of says, hey, we're having a positive agricultural impact. Postdocs and doctoral students and undergraduates that come and work with us. It is a very complex pathway, and it takes many hands to create these solutions. And I think we need to respect that sometimes good things happen with just very hard work over a period of time. I want to put this on here just for the record. These are 4 publications from last year on these catalytic oxidation and reactive filtration processes. And I want to do some conclusions here for you. I want to state that large-scale deployment of our biochar actually does present an excellent opportunity for decarbonization. Our initial results in pilot, we've also tested dosing. We haven't done the data at scale, but we wanted to see what happens when you start putting in this fistful of biochar per cubic meter of water. What happens to the wastewater treatment plant? We're adding something. Well, as it turns out, nothing. Nothing in terms of the mechanics of it, right? But in a certain sense, it's going to increase water quality, and in our particular system, increase it in a big way just if we put that carbon in there. If you remember from freshman chemistry, filter aids to increase or enhance the quality of filtration, diatomaceous earth and a few things. Carbon acts like that. I mean, how many of us have a water filter on our countertop where we filter our drinking water? The same sort of thing biochar is poor folks activated charcoal. And that's one of the reasons it's increasingly used in water treatment. But more importantly, the results demonstrate the potential of carbon negativity become as important as pathogen removal and pollutant removal. So the question I have to you, why don't we do that? Why don't we do that to address, and it's not about patents or making money or anything else, but why don't we do that as a community to start addressing climate change? Is climate change not as important as clean water? Is climate change not as important as nutrient and recovery and recycling and food security? So I'd like to also finish with a kind of a special sort of comment that I might have, and this more reflects to the larger goal and mission of the very ambitious project of EURECA-PRO. It's something that it's a global experiment in sustainability. It's something that I think the world is celebrating, that people have taken this risk on in terms of uniting the resources of 8 or 9 countries and universities together on a common track, on a common path, to share ideas, to share resources, to share the inspiration, and to also share the hard work that students and faculty have in terms of creating this new future. And so what I want to say to you as a challenge is that our future is a future of choices, and many of these will be difficult. And our choices that we make can have irreversible consequences, and we all have witnessed those in these irreversible plant and animal extinctions. We need to be wise in our choices, and the wisdom of today needs to stand the test of time for tomorrow. And I will close with that our choices that we have now will be our human destiny. So I'd like to thank you very much. I'd like to thank TUC and the EURECA-PRO people across the network, the Alliance, for inviting me here today. And I celebrate with you the promise of a sustainable future. Thank you so very much.
Thank you very much, Greg. It was a very inspiring talk and very interesting from the engineering point of view. We have some time for some questions. I hope they're tough questions. Okay, anybody from the audience? I guess.
No, I'm a faculty member. I saw you nodding quite a bit. So what do you think about the future challenges that you have in your career and your academic challenges? Is it something that you think that the current system is preparing you for the future?
I think we have to be ready for those challenges. We don't have other choices. We should change our mistakes.
Better use the microphone.
Yeah, sure. Hi. Does it work? No. Yeah?
You have to be close.
No.
No. Is it on?
Yeah, I think we don't have other choices. We should change because those challenges are coming. They have come,
Yes.
to be honest. So I think in Europe we are ready a little bit. There are new people that believes those answers. We have the technology. I think we can do it.
Good.
The only point in my mind is that we should do it slowly and in small communities. If we do it in small communities and then we split it, I think it will be more practical and more acceptable from the society.
I see.
Thank you.
Oh, good. Well, thank you so very much.
You going to give a response? Or?
No, I'm going to say I'm all in agreement, with the exception of one word. You said slowly. The one thing that I think we don't have is time. If you look at the carbon charts, carbon models, in terms of real impacts and irreversible consequences, I think that we have to adopt a sense of urgency in what we do and how we do it. And I think that's by allowing communities of development, of engineering, of new ideas to come together with those people who will eventually adopt those technologies and to share the burden of discovery and the costs of discovery and the cost of advancing this. And a lot of that is actually based in communication, that we have to be willing to talk in terms that aren't associated with science and engineering, or that personal kind of processes that it's about me. I think it's about us. It's about rethinking from a model that is about a thing to a model that is about a system of many things, which is what nature is. And so we need to have people look at not just some sort of immediate sort of consequence, but what happens over time in terms of this global and sometimes irreversible consequence. Climate change will create a very different future for you and my children than it did for me. And so it's one of those dynamics where the youth of today have to be the force of change, because it's the world that you are inheriting. And it's not necessarily that it's anyone's fault. It's all of our faults. We weren't perhaps wise enough. We never knew that we could pollute the oceans. We always thought of throwing things away without asking the question to ourselves, where is away? We've thought of single-use, single-serving containers without thinking about, well, what happens when there is no more away? And we're now in the consequence dynamic of that away is in our backyard. There's plastic at the bottom of the ocean that will be there for the next 500 years, well past your generation. So we have to come up with a responsible production and consumption cycle, the mission of EURECA-PRO, a very advanced and obviously a very needed definition. We need to reconfigure how society works and operates. The past is not acceptable, and to be honest, the present is not acceptable in terms of the responsibility that we have to future generations. We just need to do better. We need to do it practically. We need to know what the costs are. We need to all adopt a life cycle frame of mind. And I think we can change. I have to be hopeful. I have children too, and so I have to be hopeful for their futures and for their children's futures. And that's where, for instance, indigenous peoples that have lived off the land, the ancient Greeks, for example, where we live in an environment, but we are a part of that environment, that we learn from nature by understanding nature, listening more to nature than we perhaps have in the past. So I think the future that I want to leave you with is a hopeful one. And it's hopeful because of the passion that we have with faculty who have dedicated their lives to creating new solutions, and for the energies of students that are doing the hard work of learning. I think we can all celebrate this process, that discovery is in fact the ascendancy of solution, and you are part of that process. With that, thank you. Thank you.
Okay. I have two questions.
Yes.
The first one is a bit technical in a sense. Now, why do you have to go down to 0.1 milligrams per liter for phosphorus? Is there a serious problem of eutrophication? The Mediterranean Sea, for instance, is oligotrophic.
Yes.
But is it a major problem, I know, with the Great Lakes eutrophication situation? Is it that you have to go below 1 milligram per liter? Is it that important? Is this the only reason, or?
There's a couple of reasons, but one of them is many of our urban areas, many of our communities are already in areas with highly polluted waters. So at least in the regulatory consequences in the United States and what we call the National Pollution Discharge Elimination System, if you create a new discharge and you are discharging into highly polluted areas, the immediate answer is no, you can't. The system is at capacity in terms of nutrient pollution, so you're asking to add more. For example, I'll give you an example of Citronelle, Alabama. There was a discharge, a small community that needed to upgrade their wastewater treatment plant, but they were discharging into a highly polluted ecosystem. And pretty much the regulatory science said, no, you cannot do that. So you could do it if you built a 20-mile pipeline and discharge over there. Now think about that. This is a small community that now has to get the land rights and the ability to discharge, to pipe their discharge. But in fact, since 2016, they've been using this process, and their permit is the lowest in the United States. It's 0.022 milligrams per liter total phosphorus. And they've been achieving that now since 2016. So the answer is in highly polluted ecosystems that want to reverse that in the Great Lakes. And by the way, this system is demonstrated its capability to address other things. So I haven't talked about mercury. It's about the only technology maybe some membrane systems can get into the Great Lakes criteria of very low levels of mercury, which is a reproductive toxin, as you may know, especially in aquatic birds. And yes, it cleans water. But like any other process, you can tune it. So there are installations where, okay, that permit or my receiving waters only require a certain level. You turn it and dial it down and off. And so it takes either less chemical, less power, less flow through, less dynamics. But at the same time, you have to have system flexibility, because when a community comes in and they adopt an engineering solution, it has to not only address the challenges of today, but it also perhaps has to challenge the challenge of the future. And so, for instance, in the UK, they've just lowered their phosphorus levels to 0.25. It used to be at 0.5 or 0.4. And so this is actually within very recent changes. So what's going to happen is, as we ask more of our environments, those regulatory pollution requirements are going to become stricter and stricter, because we can't keep growing. Our human population is 9 billion and increasing, and so we just have to do a better job. So as engineers, we need to design systems that are flexible to address highly contaminated solutions or solutions for environments that may in the future require a higher level of treatment. So I hope that answers.
And the second question slash comment has to do with the carbon negativity.
Sure.
That you showed the results. Now, last time I checked, unless I don't know exactly where we stand right now, when I checked the carbon trading system, a ton of CO2 traded at about $70 at the time, and it had reached up to 100. However, biochar was not part of the trading system. You could not claim, a country could not claim that I produced that much. Sorry. A country could not claim that I produced that much biochar, which means I have sort of removed that amount of CO2 from the air. I would say that biochar is a very good material, very beneficial material, but my impression is that it hasn't been appreciated as much yet, not by scientists or engineers, but primarily by the people who will make the regulations. And I don't know if something had changed, or how do people see this thing in the United States?
It's changing, and it's changing rapidly. The biochar industry is growing, in the billions of dollars, and is growing worldwide, as you can imagine, because there's a lot of waste carbon that's around. And so there's a couple of things. Number one, we always have to be very wary of double counting. So who gets to count the carbon credits? Is it the person making the biochar and sometimes selling those carbon credits to Microsoft because they use high intensity carbon consuming computers? Or is it to the farmer that's putting it into their soil? So double counting and carbon accounting is a big challenge. You got to know where your carbon's coming from. So there can be the required carbon markets, which require polluters to reduce their carbon footprint, and they typically have to buy carbon credits. And the voluntary carbon market, where people are doing it, or companies are doing it for goodwill, because they want to be a part of the solution. So it's changing rapidly, and I'll tell you that the biochar industry has been responding to that by actually issuing insurance policies into the carbon marketplace. The carbon marketplace is rapidly developing, but if I can, as a manufacturer, ensure to you that you are purchasing X, which has X amount of biochar, which has X carbon value, and therefore getting some sort of, that I'm ensuring the transparency, and that's the key word, the transparency of the transaction. And in fact, I talked about carbon net and also carbon 100 in terms of what the exact value is. they're now finding the most recent literature is saying that it is closer to carbon net than it is to carbon 100 in terms of the mineralization dynamics of biochar in soil. So it's rapidly developing. There's a lot of industry, especially in what I'll call the tropical regions that produce a lot of carbon biomass just because of their location. And so the marketplace for biochar is increasing. The potential for it to be used, and one of the top uses, in fact, the top use I think is developing into water treatment. And if you just put it into any sort of water treatment system, and remember that wastewater treatment especially is a lot of times settling solids or removing biosolids out. In fact, we worked with a company, Bioforce Tech, and we've used their product, their biochar, which is biosolids that have been pyrolyzed and created their own biochar. So think about that as possible. They're creating all this organic waste. They're pyrolyzing it, using it on site potentially to help clean the water in a very circular economy there. Before actually having to waste it or transport it as a waste material. Good.
Thanks.
Yep.
Any more questions, comments?
We're running out of battery.
Thank you. So thank you for your presentation. I have actually a double question, two short questions. The first one, on your system, do you regenerate biochar when it reaches its maximum potential, or you just put in new biochar to the system?
To answer that really quick, we use it once. And so there's two ways we can collect it. We've used it as a collector in front of the process and let it kind of dribble through. But if we want to do large grain biochar and absorb nutrients and also expose it to ozone, we do it in that fashion. We also can just directly discharge it into the secondary treatment processes to affect and go into the normal biosolids process. So so we don't treat it like activated charcoal. We treat it as a water reagent at those, and again, the cost was working out for us in large-scale implementations of 1 MGD, 1 million gallons per day. It was about 3 cents per cubic meter. And probably there are efficiencies of scale in terms of where the biochar marketplace is going and a few other things. But so it is not like activated charcoal. We're regenerating. The energy cost of that, of reprocessing, is not beneficial. But what we're trying to do is actually just provide a useful use for a material that directly impacts climate change and climate sequestration. So the concept of reuse would be something that we want to reuse and conserve. To be honest, if the more wood waste, crop waste that we char, use in any sort of process to enhance its value, because there's a cost to doing any process. So if we can use it to make cleaner water, if we can use it to make more fertile soil and bury it, and that helps sequester it, then we're not addressing it like a commodity where we have to recover its value and reuse it. We're addressing it like as a carbon sequestration technology. And so in my mind, if you look at some of the carbon capture devices, I think they just opened one in Iceland or Greenland, I believe, the big refrigerators that are 10 stories tall with the carbonate technologies. Those are wonderful, they're practical, and in fact the carbon market value of the ton of carbon from that goes up to as high as $1,000 per ton. But it's a lot of machinery, a lot of footprint to do what you're doing there. So we take an alternative approach that biochar is taken from a waste stream. And you got to remember that when we take carbon materials from the waste stream, we also keep them from rotting in the field or being combusted actually as forestry waste, where it produces a lot of greenhouse gases as well. So as it turns out in LCA, when we looked at that, the wood waste avoidance is actually a very large contribution to this. So it's not just the biochar carbon, but it's the avoidance of wood waste that actually contributes greatly to the overall carbon negativity. So one use is good, and the best cycle in terms of addressing overall LCA and impact for the future.
So, if I understood correctly, you just leave it be in the effluent stream, or you collect it at the point of the filtration.
You got to remember, especially in wastewater treatment plants, there's biosolids collection apparatus. The engineering is all capitalized and paid for, and we're adding small amounts of material on a relative basis, and it's the system is addressing it. Probably takes out some things. So even if we just use it to clean tertiary water, but then as a disposal mechanism, return it back into secondary, it settles out in some of the unit processes in that plant. We're all done with it. It goes off, even at biosolids, if it gets land spread like normal biosolids do, or gets put in a composter or other sorts of processes out there across the world. At that point in time, it's mineralized carbon, so it's got its 200-year, 300-year life cycle in terms of sequestering carbon. So we're done with it. We can kind of count that as a positive in terms of carbon accounting. Okay? Good. You bet. Thank you.
Okay, Greg, thank you very much for your very interesting presentation. We're looking forward to seeing you again here.
Good.
Okay, and I think it's time to break.
Okay.
Thank you very much again.
Thank you. Thank you.